So we're going to look at the quotient rule in this video, and the quotient rule gives us a method that allows us to differentiate algebraic fractions. So quotient means that we're dividing one function by another. And so if we've got y equals f of x over g of x, we're dividing the function f of x by the function g of x. Now we can rewrite this as a product of functions, and then we can apply the product rule that we discovered in the last video in order to derive our quotient rule. So we can rewrite y equals as f of x multiplied by the inverse function of g. Now, for our product rule, we know that y prime equaled f prime g plus g prime f. So f for this function is going to be the function of x, and that means f prime is going to be the derivative of the function of x, and g is the inverse function of g of x, and so g prime is going to be -1 multiplied by the square of the inverse function of g of x, and we're going to multiply that by the derivative of g of x using the chain rule. And then we're going to simplify this by writing negative derivative of g of x divided by the function of g of x squared. Now, our product rule was y prime equaled f prime g plus g prime f. And we're going to substitute in the information that we've just created. So f prime is the derivative of the function f of x, and g was the inverse function of g of x, and we're going to write that as 1 over g of x. Then we're going to add on the derivative of our second function, and that was negative the derivative of g of x over the square of that function, and that's multiplied by our function of x. So in order to add fractions, we know we need to have a common denominator, and our common denominator is going to be g squared x, and then we need f dash x, and we need to multiply that by the function g of x, and then we're taking away the derivative of the second function g dash x multiplied by the function of x. And that's our quotient rule. So to simplify that, in our Lagrange notation, we can say that the quotient rule is y prime equals f prime g take away g prime f all divided by g squared. And we need to know this, but we can also remember that we can always derive it by using our product rule. Now, in Leibnitz notation, instead of using f's and g's, we're using u's and v's. And so what we're saying here is that dy by dx is going to equal the derivative of the first function, so that will be du by dx multiplied by the second function, and then we're going to take away the derivative of the second function, so that will be dv by dx multiplied by the first function, which is u, and we're going to divide the whole thing by the second function squared. Or, more simply put, we can say that y prime equals u dash v minus v dash u all over v squared. So let's look at a couple of examples. In the first example, we want to find the derivative of 3x plus 1 to the power of 4 on the numerator divided by 5x minus 2 cubed. So the first thing we're going to do in our Lagrange notation is identify what f and g are. So f is going to be our numerator, and g is going to be our denominator. So f is going to be 3x plus 1 all to the power of 4. So f prime is going to be 4 multiplied by 3x plus 1 cubed, and then we need to differentiate the inside of the bracket for our chain rule, so we're going to multiply that by 3. And that gives us 12 times 3x plus 1 all cubed. Now, g is going to be our denominator. So that's going to be our 5x minus 2 all cubed. So g is going to be 5x minus 2 all cubed. So g prime is going to be 3 multiplied by our 5x minus 2 squared multiplied by 5, which is the derivative of the inside of the bracket. And so g prime is going to be 15 multiplied by 5x minus 2 all squared. So in Lagrange notation, I know that y prime is going to be f prime g take away g prime f all divided by g squared. And I'm going to substitute in my values. So f prime was 12 multiplied by 3x plus 1 cubed. And g is 5x minus 2 cubed. And I'm going to take away g prime, which was 15 multiplied by 5x minus 2 squared, and multiplied by f, which is 3x plus 1 to the power of 4. Now my denominator is g squared, so I'm squaring that 5x minus 2 cubed bracket, and so that means I'm going to get 5x minus 2 to the power of 6. Now I want to factorize that numerator in order to be able to simplify. So the highest common factor of 12 and 15 is 3. The highest common power of the 3x plus 1 bracket is 3x plus 1 cubed. And the highest common power of the 5x minus 2 bracket is 5x minus 2 squared. Now I need to work out what is going to go inside my bracket now that I've taken out the factors. So 3 times 4 will give me the 12. I've got all of the 3x plus 1 cubed, but I need an extra 5x minus 2 to make the 5x minus 2 cubed. Then take away 3 times 5 will give me the 15. This time I've got all of my 5x minus 2 brackets, and I need an extra 3x plus 1 bracket to get my 3x plus 1 to the power of 4. And that's all going to be divided by that 5x minus 2 to the power of 6. Now you can see I've got a common bracket that I can now cancel down with that 5x minus 2, because I've got a 5x minus 2 squared bracket on the top, which will cancel down to 1, and my 5x minus 2 to the power of 6 bracket that will lower the power to a 5x minus 2 to the power of 4. So my next step is to expand and collect my like terms of that final bracket on the numerator. So I'm going to end up with 3 times 3x plus 1 cubed, and 4 times 5x gives me 20x, and 4 times minus 2 gives me minus 8, and minus 5 times 3x gives me negative 15x, and minus 5 times positive 1 gives me negative 5, and that's all over 5x minus 2 to the power of 4. And the final step is to collect those like terms together. So y prime is going to equal 3 times 3x plus 1 cubed 20x take away 15x is 5x. Negative 8 take away 5 is negative 13. And that's all over 5x minus 2 to the power of 4. My second example, I'm going to differentiate y equals 2x plus 1 divided by the square root of 2x minus 1, and I'm going to use my Leibniz notation. So Leibniz notation uses u's and v's. So u will be my numerator. So that's going to be 2x plus 1. So u prime is going to be just 2. And v is going to be the square root of 2x minus 1. Now that's not in a differentiable format, so I'm going to have to rewrite it as 2x minus 1 to the power of a half. So now I can differentiate v. So v prime is going to be, and it's going to be a half multiplied by 2x minus 1, and we're going to lower that power by 1, so it'll be negative a half. And we're going to multiply that by the derivative of the inside of the bracket, which is 2. And you can see that my 2's are going to cancel out. And I'm going to rewrite that as 1 over the square root of 2x minus 1. So my product rule for Leibniz notation is y prime equals u prime v minus v prime u all over v squared. Now you can see I've got a fraction for my v prime, so I'm actually going to rewrite that as 1 over v squared, and then I'm going to open my brackets, and I'm going to have my u prime v minus v prime u. So v squared is the square root of 2x minus 1 all squared, so that cancels out my square root, so I'm going to have 1 over 2x minus 1. And inside my bracket, I'm going to have u prime, which is 2, multiplied by v, which is the square root of 2x minus 1. And I'm going to take away v prime, which is 1 over the square root of 2x minus 1, multiplied by u, which is 2x plus 1. And I'm going to put that in a bracket because I'm taking away the 2x plus 1, so I need to be really careful with my signs. So I need to have a common denominator inside my bracket in order to be able to do the subtraction. So I'm going to have 1 over 2x minus 1 still outside my bracket, and my common denominator is going to be the square root of 2x minus 1. So I need to multiply the 2 times the square root of 2x minus 1 by the square root of 2x minus 1 to make that an equivalent fraction. And so I'm going to have 2 times 2x minus 1, and that's going to be take away 2x plus 1, keeping it in a bracket still. So now I'm going to multiply out the brackets. So my numerator is going to become 2 times 2x is 4x, 2 times negative 1 is minus 2, then I'm going to do negative 2x, and then it's negative 1 times positive 1, minus 2x minus 1. And that's going to be over just clear that up. 2x minus 1 multiplied by the square root of 2x minus 1. Now, if we choose a different color and go over to one side, if you think about it, if we've got 2x minus 1 to the power of 1 multiplied by 2x minus 1 to the power of a half, remember we add our powers, but we can't have mixed numbers, so we're going to have to change that to a 2 over 2. So it means that when I multiply those brackets together, I'm going to get a 2x minus 1 to the 3 over 2, and I know that I can rewrite that as the square root of 2x minus 1 all cubed. And that's what my denominator is going to be. So my denominator is going to be the square root of 2x minus 1 all cubed. And so the final step that I need to do in order to work out my dy by dx, or my y prime, I gather my like terms on the numerator. So 4x take away 2x gives me 2x, minus 2 take away 1 gives me minus 3, and that's all over the square root of 2x minus 1 all cubed.